Hello, everybody, and welcome to today's web conference. I'm Amber Rhodes from EUCI, and I will be your host today. You have logged into the Lightning Threat Oil and Gas web conference. With that, I would like to introduce our speaker for today. We have Peter Carpenter, who is the Director of Applied Engineering at Lightning Eliminators and Consultants. He has more than 26 years of experience in electronic engineering and lightning protection. Since 1988, Mr. Carpenter has been the Director of Applied Engineering at Lightning Eliminators and Consultants. Parts of his responsibilities have been applying his expertise in site surveys and analysis, and as a consultant, Mr. Carpenter has assisted in numerous field evaluations to solve past bonding, grounding, power conditioning, and lightning-related electronic failures. With that, I would like to welcome and turn things over to Peter.
Well, thank you very much. It's a pleasure to be here and to give you a little review on what we see as a threat for a lightning and the lightning environment to the oil and gas industry. Let me just give you a few moments on my company I've been working with for the last 20 plus years. Lightning Eliminators and Consultants. We also go by the acronym LEC. Has been around really since the early 1970s, really with the goal of providing unique and innovative technologies to a very industrial application such as oil and gas industry. That particular industry has unique problems and can feel a significant effect created by a lightning event. And the influence of a lightning can be devastating as far as impacting the normal operations of any oil or gas facility. Really our founder of the company really wanted to bring unique and innovative design approaches and alternatives in lightning protection to really solve those very aggressive and important problems that can be seen in that particular industry. So with that said, in the 22 years that I've been doing this, I have spent the bulk of that time working in that particular environment, mostly in the area of Texas and Oklahoma, as probably my predominant area of exposure. Obviously, one reason because of the nature of the fact that the oil and gas industry is pretty pronounced and probably a hotbed of that as far as in the United States, as well as what goes on the Gulf Coast and on the offshore platforms in the Gulf of Mexico. So with that said, I've got a number of slides here that I'm going to walk you through, and really in trying to understand what we can do about protecting a facility or a site or an application from the effects of a lightning strike, we first really have to understand the lightning event itself. So the first part of my discussion will be to break down the actual lightning itself, how it's formed, part of the lightning discharge process, how the lightning discharge process will then impact our operating systems, our electronics, our command and control systems. And once we understand that, then we can look at conventional methods of dealing with lightning protection, their limitations, and then look at some alternative methods and that we can pursue in trying to minimize or in reality, totally prevent lightning-related outages and negative effects at a facility, again, caused by a lightning strike. So with that in mind, we're going to start with the first few slides, just kind of laying the foundation out here of what we can have. First of all, some brief facts about lightning itself. Of course, one strike can cost millions in damage, downtime, product loss, and liability. We've been involved with a number of large oil and gas companies where they have expressed to us that one single outage, for example, it could be a refinery, one single outage of a lightning strike, shutting an operating unit down, could literally cause hundreds of thousands of dollars in damage, either in the loss of that product, having to flare the product, or lost revenues in actually producing the product, and, of course, the safety risk that goes with it. So depending on the application, the fact that we can approach $1 million, in fact, I've got one example I'll show later on, or it was approaching $10 million is something that can actually be seen by one individual lightning impulse. Lightning does not discriminate. It really does strike anything in its area of influence. Every lightning strike itself has what we'll call a strike zone, and anything inside that strike zone can and over time probably will be struck by lightning. So the old maybe tale of, well, lightning will always strike the highest structure. It might be more vulnerable, but won't necessarily collect all the strikes. If you have a situation where you really can't predict a lightning strike, for example, there are some tools that we can use to estimate our risk. For example, NFPA 780, that's the National Fire Protection Association. The 780 standard does have a risk assessment in there. But even that risk assessment, in which you look at the number of lightning days you have, flash density, you look at your land mass you have, how much land mass do you have in your area of concern, what's the height of those structures, what's their explosive capabilities. There's basically a small equation that you use, and you can plug all those coefficients into that equation, and it can tell you, yes, that you have a lightning risk of being struck, but it's not going to tell you that you're going to be struck each year, once a year, or each year 3 times a year, or once every 10 years. There is no really software design that you can use to say, we know exactly what a risk is and how many times they're going to be struck. That really doesn't exist. Lightning does strike more than once in the same location. You may have heard the story, well, lightning never strikes the same place twice. Very wrong. Typically, your higher structures will be more vulnerable to lightning and therefore collect strikes possibly more than once during one storm. I've had some discussions with some broadcasters who have a TV antenna that might be 1,000 foot in elevation, and they've described seeing that TV tower get struck 2 or 3 times during the same lightning storm. So lightning does strike more than once. Of course, at a certain object or location, but what weighs into that is, of course, how tall is it, isochronic level, how many thunderstorm days you have, and other influencing factors. Now, in this slide here, we get a quick kind of review of what the threat is to lightning itself. Some brief review of what we're seeing as far as risk. For example, the first bullet, 15% increase in lightning-related losses from 2009 to 2010. That comes from Lloyd's Insurance. Now, that's based on some 2011 data. My first estimate of why that's occurring is because we're seeing a greater use of sensitive electronics every year as we grow. So therefore, as you increase your electronics in the field, in the area in which you can have lightning, the more electronics you have, the more sensitive electronics you have, whether it be instrumentation, command controls, DCS, PLCs. All of those are going to be very vulnerable to lightning. So as you use more and more of them, your risk grows, and therefore your potential damage grows. In 2008, the cost of lightning damage and related losses exceeded $5 billion. This is coming from the National Lightning Safety Institute. And it's a 2009 data, but you can see that there's significant loss in revenues and cost in lightning activity. Another interesting side note here is lightning accounts for about 61% of all accidents in storage and processing activities. That's, of course, where natural events are identified as the root cause of the incident. In other words, they could say the root cause wasn't necessarily a man-made problem, but was a natural, God-made problem, lightning being the major problem. In North America, 16 out of 20 accidents involving petroleum product storage tanks were the results of lightning strikes. Again, so in the storage industry, and what we're seeing more and more in the last 2 or 3 years is a significant increase in the storage capability of petroleum in the United States. A lot of the oil futures are dependent on people speculating on the oil price, and what's happening now is we're seeing a significant amount of oil tanks being built throughout the U.S., so these speculators can basically buy oil and store it, buy it low, sell when it's high. And we're seeing a significant growth in tank production throughout the United States. And Cushing, Oklahoma's had a very big increase in their tank volume as far as storage. And other locations in Texas have seen the same growth, where we're seeing more tanks storing petroleum-based products. And therefore, as these tanks grow throughout the U.S., the exposure to a lightning event happening somewhere and creating a tank fire obviously is increasing with the growth of those tanks in the United States. Now let's talk about the lightning discharge. Let's lay a little foundation about really what is going to generate a risk and really how is lightning going to form. Let's start as most kind of basic principles. Let's talk about basically how we generate a charge in a cloud. Now, what is creating this electrical event? Well, it's quite simple when you think about it and you break it down in some basic terms as expressed in this slide. First of all, we're going to talk about some water droplets inside the cloud, water, wind. That's another part of our formula, if you will, our recipe. We're going to have frozen water drops develop. We're going to have hail. We got the natural effect of gravity in the earth. We have a collision effect. We also have electronic collection effect. And then we're going to have charge separation. So what's all this mean? Well, during a electrical storm, as we're having a thunderstorm approach our area of concern or develop over our area of concern, we're going to have water inside our clouds. Obviously, in most cases, we're going to have moisture accompanying a thunderstorm. We have water, rain inside the cloud. Now, we're also in a cloud. We have a lot of wind turbulence. If you've ever been flying in an aircraft and you're flying around an electrical storm, you don't want to fly through it. You probably had the uncomfortable feeling of a lot of turbulence, a lot of wind. There's a tremendous amount of wind turbulence inside a thunder cell as part of the natural event of an electrical storm. Well, that wind turbulence is going to pick up those water droplets and hurl those water droplets in an updraft from, let's say, the bottom portion of the thunder cell to the top portion of the cell. Now, we're going to have significant temperature variation from the bottom of the thunder cell to the top of the thunder cell. For example, you could have what we call a giant thunder cell, which the top of that thunder cell cloud is approaching 50,000 feet in elevation. Obviously, it's even so high an aircraft can't fly over it. They're topping out about 35,000 plus feet. So that's why you have to vector around a storm in an aircraft. Well, you might be at the base, maybe you're at 20,000 feet. Well, you have 30,000 feet of storm cell from the bottom of that cell to the top. Well, you take that moisture in the cloud at the bottom, it picks up some upward moving wind, and as it's hurled upward in the cloud, we have temperature variation, which takes that water droplet and actually freezes it. And now it becomes basically an ice sliver and eventually gains in mass and becomes hail. Now hail gains in mass and becomes heavy. It now feels either natural effect of the gravity or wind pushing it down, and it plummets now back down through the storm cell back towards the earth. Well, as that hail plummets back down through the storm cell, it will collide, have a collision effect with upward moving hail or ice slivers. Now, as we have that collision effect between hail and ice slivers, we're going to have the hail collecting an electron from an adjoining ice sliver during that collision effect. It actually captures an electron from that ice sliver or hail. And as it captures that electron, it basically collects more electrons, which gives that particular atom a negative charge. So what we have basically is a dynamo. Our thunder cell is a dynamo. It is a cell generating power, electricity, by the natural effect of wind, moisture, temperature variation, Hale generation, collision effect, electron collection, and then charge separation. So that's our basic recipe for what's creating a charge inside a thunder cell. Now, let's talk briefly, because I mentioned about electron capturing. I'm going to throw a couple slides out here. Hopefully, it's something that might take you back to maybe your middle school or maybe high school, probably actually more towards middle school, about the atom and what an atom is, and electrons, protons, neutrons. But the reason I want to bring this next couple bullets up in a little illustration of an atom is, during our discussion, we are going to talk about charge separation. We already briefly did so. And we're going to talk about ionization effect. What's an ion? What's an ion? What's ionization? So I thought it'd be nice just to kind of give a very simple explanation here, well, hopefully simple, on what we're talking about. Let's break it down in pretty simple terms. For example, let's start with the atom. The center of the atom is positive charge. Now, electrons, I mentioned, have a negative charge. Electrons move around the center of the atom. The positive charge of the atom pulls electrons towards the center of the atom. Now, remember now, the old adage of opposites attract goes back to basic fundamental. Negative and positive. Protons and electrons attract to each other. They want to come together. So when your atom is basically positively charged, the electrons are kind of pulled towards it. Again, we're mentioning by opposite charges attract. So let's take it down to the actual atom illustration here. Here's our atom. You can see that in the center of the atom, you have basically your protons illustrated in the blue circles, if you will. Your neutrons are basically the center part of your atom. And then your electrons are kind of rotating around your atom, being sucked in towards the atom by the positive charge. Now, if that particular atom has the same number of protons as it has electrons, it has a neutral charge, meaning it really has no charge, positive or negative. But once we add an electron, which is negatively charged, to that atom, and we have one electron more than we have protons, that atom now has a negative charge. So going back to my charge separation discussion, what creates that charge separation in the thunder cell? As the ice slivers collide with the hail, they capture an electron. That means now that particular hail that captured that electron now has a negative charge. Now that ice sliver that's going up towards the top of the cloud has one less electron, which means now it's left with a positive charge in that atom. That's again kind of breaking down the basic charge separation, as well as give you an idea we're talking about charge of an atom. Let's break it down a little more. So again, if an atom has, I guess in review, atom has the same number of protons and electrons, it has a neutral charge, no charge. Has more protons, positive charge. More electrons, negative charge. Now, what is an ion? Because we'll talk about ionization later on in this discussion here, about the next half hour or so. So let's kind of do a brief discussion. An ion is an atom or a molecule which total number of electrons do not equal the total number of protons, which result in a negative net or positive charge. So in other words, if I got more protons, positive charge. More electrons, negative charge. Again, we'll talk about that briefly too. Now, when I talk about ionization down about 15, 20 slides from now, I'm going to be talking about the physical process of converting an atom to an ion by adding or removing a charged particle such as an electron. So when we talk about ionization, we're going to talk about adding electrons to an atom, making it negative charge, or adding a proton. So we're actually talking about physically changing the molecular structure of that atom by adding or subtracting a proton, the ionization process. So again, you may want to refer to that later on, but that's the basic discussion about when I say we want to talk about our ionizer or ionization, we're talking about that physical process of converting an atom to an ion, which means one more electron or one less, by removing a charged particle. Hopefully I didn't go over your head, but I thought that was kind of important to kind of lay that basic foundation for charge separation, how we develop a charge. In fact, in this slide, you're going to see an example of a thunder cell that is now ready to discharge. You can see that we've had the scenario in which we have had our electrical storm develop. We've had that wind, temperature, moisture, hail, ice sliver collision, electron collection. So now you can see the base of my thunder cell is negatively charged, meaning that those atoms have more electrons. The top of the cell is now positively charged. Those atoms up there have more protons than electrons, all caused by this effect of lightning or charge separation, I should say, discussed in the first couple of slides. So now we have this charge separation developed in the thunder cell. Now what happens is the Earth, directly below that thunder cell, also the Earth-bound structures below the thunder cell. For example, if we had a building in this area here, it would collect that positive charge. If we had a derrick there, if we had a platform there, it would also have a positive charge forced on that structure caused by the negative potential on the base of my cell. So here's my thunder cell, my cloud. We like to call it a cell, like a cell of a capacitor. It really is a capacitor holding coulombs of charge. Again, we're going to have positive potential clustered at the upper portion of the cell. We're going to have negative potential at the base of the cell. The magnitude of that negative potential actually forces a positive charge on the Earth and all structures below that cloud. House, building, tower, derrick, tank will have that positive charge forced on it. Also occurring during this natural event is a very high electrostatic field developed. That's basically a electrical charge in the air. In order to have lightning develop, a lightning flash, scientists have concluded that you need somewhere between 5 as a minimum, could be as high as even 30,000 kV. So 5,000 volts to over 30,000 volts a meter of static charge in the air. Now, that means basically, if you had a voltmeter and you had your voltmeter probes and you separated the two probes of your voltmeter, and that voltmeter was designed to measure electrostatic field intensity, if we had a lightning event, strike developed, we have to have at least 5,000 volts per meter. It could be high as 30 kV. So we have a very tremendous potential in the air. In fact, if we were to measure from the Earth to the cloud with an electrostatic voltmeter, we would measure somewhere around 10 to the 8 volts, plus or minus 10%. So basically 10 with 8 zeros, maybe 10 with 9 zeros after it, 1 billion plus volts of potential between the positive and the negative charge. Now, we've talked about briefly that we showed you that that the electrons are negative and protons are positive, and they're attracted to each other. Negative and positive charges are attracted. They want to come together. They want to short out. Well, what is preventing that negative potential that's on the base of the cloud and the positive potential on the Earth and the Earth-bound structures? What's preventing those two opposite charges from coming together, from shorting out? Well, we look at that. The only thing that's between that positive and negative potential is the air itself. The air is what we call a dielectric. It actually has an insulative value. It's an insulator. But it only has a certain amount of insulative capabilities to a certain dielectric, certain voltage potential. During a mature electrical storm, when these electrostatic fields become so great, starting at 5 as a minimum, going up to 30 kV as a maximum, the air, which is trying to work as a buffer, saying, hey, you positive and you negative, you can't come together, is trying to hold them back and saying, you can't short out. Eventually, what happens? The air can no longer work as an insulator, and it breaks down. It conducts. It actually starts to conduct like a wire, a conductor would. And now this next slide here, you're seeing that we've now kind of put in there our same thunder cell. We have our positive potential, we have our negative potential, and we have now, you can see here, we have forced a positive charge on this offshore platform. So the cranes, living quarters, the deck have all taken on a positive charge, as well as the sea itself. It's all charged with the same potential. Now we have this lightning bolt, we call it a leader, formed from the base of the cloud, propagating down towards the Earth and the earthbound structure. Now, as I mentioned on the previous slide, if we were to measure from the, say in this case, the sea, to the base of that thunder cell, for this example, let's say it was 10 to the 8 volts, 10 with 80. That was my voltage potential pre-strike. Now, when this leader is formed, this lightning bolt, we like to call it a step leader, is formed, it's propagating down towards the Earth in a very arbitrary fashion. It has branches to its circuits, all kind of reaching out, trying to find a place to hit, if you will. Now, this is what we like to call a conductive ionized path. It's basically a conductive electrical path coming down from the cloud. In simple terms, it's like bringing a conductor down from the cloud towards the Earth, which means that if I had 10 to the 8 volts pre-strike, if I was to measure from the cloud to the sea with a voltmeter and it measured 10 to the 8 volts, that means as I'm bringing this conductor down, I'm bringing down with it high potential of 10 to the 8 volts. Well, let's just say for this illustration, this cloud was 10,000 feet above the platform. So now I have a lightning strike developed. It's going down from 10,000 feet, 9,000 feet, 8,000 feet, 7,000, 6,000, 5,000. Now I'm going to get within a few hundred meters of the Earth, sea, and the platform. Now, if I have the same 10 to the 8 volt potential, but now my air gap between the tip of that leader and, let's say, this derrick here is only a few hundred meters. If I've got 10 to the 8 volts but a few hundred meters, what has to happen is the kilovolts per meter have to increase to a point where it actually will exceed 100,000 volts per meter. Again, the reason being, I have a very high potential of 10 to the 8 volts. My air gap now is only a few hundred meters. That means my kV, kilovolts per meter, in that area of influence will reach and exceed a threshold of 100,000 volts. Why is that important? Well, that's where scientists have concluded that at 100,000 volts potential, even before this lightning bolt will reach the Earth or an earthbound structure as seen maybe by a building or tower in this illustration, multiple counter leaders will be developed off of the Earth and earthbound structures. Here again, we're showing you that all these counter leaders are coming off of the building, this tower, this tree over here, and another tower. All of these are all trying to, what we like to describe as, win the collection race. One of these actually will do so, will actually win the race. Let's just say it's this particular streamer over here. He's going to reach up here, win that race, and actually close that circuit midair. Now, once we have actually had this switch closed, we've determined the point of collection. Now we're going to have determined where all that energy is going to flow. Now we've determined who's going to get struck. And now all the tremendous amount of energy, current, voltage, is going to be from that cloud is going to be shunted down that closed electrical path through that building to ground. For example, many of our existing standards we use right now are designed to be efficient streamer generators. For example, if you see a lightning rod on a building, a lightning rod is there as a efficient streamer generator. It wants to develop a streamer very quickly, outcompete any other streamer in its area of influence, win that race, and bring that lightning bolt to that lightning rod, also called an air terminal, and take it to ground. Now, lightning rods are rather effective in doing that. In the typical design, and I'll touch briefly on these later in the discussion, through NFPA 780 or UL 96A, lightning rods are about 90 to 95 or maybe even 98% effective of collecting all strikes in the area of influence of their protection and bring that lightning strike to the terminal and taking it to ground. The other, let's say if you had 10 lightning strikes to that building, one of those might miss a lightning rod and hit the building itself, causing some structural damage and electronic damage. So they're very effective in collecting lightning strikes. The downside is, and we'll talk about this in the next few slides coming up, is that they also invite into that area in which, if we're in a gas facility, a chemical processing facility, a refinery, we have all our sophisticated electronics, our command and control systems that are running digital and analog circuits. We're all now inviting a very high voltage and current impulse into an area that would reflect that voltage and current onto our low voltage instrumentation data lines, current loops, analog circuits that will now create either a false signal or lost electronics damage, if you will. Now, this next slide basically talks about there is going to be a strike zone. Every lightning strike has its own equivalent strike zone. And I won't spend too much time on this particular slide because it really doesn't have a lot of bearing on our discussion as far as how we can protect ourselves against lightning, except to say that all the standards that we typically use, that we'll see in the industry today, have a design criteria which has to consider a strike zone. Now, what we're saying with a strike zone is that a lightning, and we'll talk about some characteristics of lightning down the road in a few more slides, but as a quick introduction, lightning current, the amount of current that we can see in a lightning strike, can be as low as 2,000 amps. Really not that much, very minimal amount of current. We can see a lightning current in excess of 200,000 amps, so the other side of the spectrum. So you can have as low as 2,000 to over 200,000 amps in lightning current. Our average lightning current is around 25,000 amps, 20, 25, 30,000 amps. That's the most average lightning current we're going to see in a lightning impulse. Well, taking two examples, let's say our first one is an average lightning current, let's say around 25,000 amps. Our 25,000 amp lightning strike has what we call a step length of around 30 meters. So when you look at a lightning bolt and it's coming down from the cloud, it's going to propagate down. Let me see if I can draw here. It's going to come down kind of like this, step lengths. Now, these steps, and again, a pretty rude design here, apologize for that, but those steps are equal in length, and they're going to be based on the current in that strike. So the more current we have, the greater step length. For example, my step length for a average lightning strike of around 25,000 amps is around 30 meters. So it's rather small. But now let's take an example of my lightning strike current of over 100,000 amps, which if we had 100 lightning strikes to this building in the course of, let's say, 1 year, which is not going to happen, but we'll use it for illustration purposes. If it took 100 strikes to this building, 10 of those would be around 100,000 amps or greater. So about 10% or over or around 100,000 amps. But let's use that illustration. 100,000 amp lightning strike, rather rare, but they do occur, has a step length of around 120 meters long. So its step length is significantly longer. It's going to be somewhere looking much more like that, longer length. What's that do? It impacts the strike zone. The longer your step length, the greater your strike zone. For example, your 25,000 amp lightning strike has a strike zone around 30 meters. So, example, when this lightning bolt comes down, it reaches what we like to call and describe as a point of discrimination. And it's illustrated by this little red dot right here. the point of discrimination basically means that next step length, which is going to be around 30 meters, will initiate the upward streamer that will collect it. Let's say, for example, this tower was 20 meters away. It's inside the strike zone. This tower over here, which may be taller, is 50 meters away. Well, it's outside the strike zone. It'll never collect a strike. So in this case, this tower probably got hit over here. But now let's take the second example of a 100,000 amp strike, which has a much wider now step length. It's 120 meters. So now all of a sudden this tower, which was higher and 50 meters away from the point of discrimination, is now well inside that strike zone, and therefore would develop a streamer, and because of its height, most likely would collect a strike. So again, when we look at all our lightning rod design, we have to make sure that we capture both lightning strikes that are going to be either low current and have very small striking distance of a few feet, or high current and have a striking distance of over 100 meters. Now, this next slide here, and you can go ahead and play the slide if you wish, actually illustrates the example of a lightning strike. And I want you to show you how it discharges and how big the branches are and how large the area influence is as it goes across the horizon, looking for a streamer to collect it. And you can see the streamer that collected it was the one that now, you can see the discharge, and it's flashing right here. That particular point was the one that won the collection race. All the energy is now flowing into that channel. And when you saw the lightning bolt light up and flash, that's showing you what we call a multiple dart leader and return stroke effect. In fact, if you wouldn't mind, let's play that one more time if possible. And you're going to see that as it propagates across the sky, it's looking for a place to be collected, and once it's been collected, all the energy flows in that one channel, and now it's going to flash a couple more times, and that's as more energy from the cloud flows down that ionized path, and we have a couple of what we call dart lead or return strokes from just one lightning strike. There's never really just one surge of current. There's multiple surges of current in typically one lightning strike. In some cases, you can see up and over 20 current surges. Again, you can see the flickering effect in that particular illustration. I also wanted to show you again that the area of influence to collection was quite pronounced. It was literally over a mile of what could be collected, a mile of influence of where that streamer was going to come from that was going to win that race and collect a strike. Okay, moving forward. So that kind of gives you a very good visual of the lightning strike itself. Now, this slide here, we've kind of taken a similar lightning event. We've slowed it down, still framed it, if you will, and so you can see a snapshot of one lightning strike itself. As you can see here, you have a couple things occurring. First of all, the red arrows are pointing to upward streamers that were trying to win the collection race. These streamers here did not win the race. In fact, there's one over here that was very pronounced, didn't win the race. The one streamer that won the race is actually made that electrical connection, and now we have a closed electrical path. So again, we see this one slide, first of all, is that yes, that each lightning strike does develop multiple upward streamers trying to compete to win the race. Secondly, I'd like to point out is that you can see that this lightning bolt has a branch circuit. It's got these little fingers going quite a ways looking for a point of collection. In some cases, they could be over a mile away. They could win that collection race. Now, one of the questions we might have is what kind of damage can occur to a lightning rod or terminal from a typical lightning strike? Well, lightning rods, and I'll show you some examples of lightning rods again further on in the discussion here, they're designed to be able to take even the worst case lightning strike current, for example, that 200,000 amp strike, if the system is designed correctly and installed correctly. Even though we're talking a lot of current, 200,000 amps, the actual time duration of a lightning strike is microseconds. So we're not talking about a lot of energy over a long time. It's a lot of energy over a short period of time. So the cables used in a standard design system, lightning rod type design, is designed to be able to handle that high current, even up to a 200,000 amp impulse, with really nebulous effect on the system. Now, lightning rods come in two versions. A typical lightning rod comes in two versions: a sharp point and a dull point, a blunt point, also called a blunt point. The sharp point, I have seen air terminals, lightning rods, that have been pitted over time. If you're talking about a sharp point air terminal, lightning rod, same thing, you could see that you might actually have a pitting effect on the edge of the terminal, or you could see, and I've seen some cases where it looks like that tip has been almost melted. So you could see maybe some small effect to it, but reality is, as far as performance goes, it's really a nebulous effect. It's not going to affect the overall performance negatively as far as being a collector. It will still generate the streamer. So, again, lightning rods are designed to really handle the strike. Now, the key that you can have those still with the lightning rods is it does not mean that if you put a lightning rod system in, you still will not have damage. The system itself might not be damaged, but you could have a secondary effect damage your electronics, or you could still have an explosion because vapors are present, and you have an ignition source. We have provided a significant amount of lightning protection at gas processing facilities that will either be Class 1 Div 1 or Class 1 Div 2, and they're going to have vapors present either all the time or part of the time. And if you've got a lightning strike in an area where you have vapors and you have oxygen, you have the ignition source now. You've got the spark. And there might be existing lightning rods there, but they're not going to snub out that spark. And you will have and can have an explosive event. Now, let's talk about we mentioned in the video illustration of a dart leader return stroke. Now, as you see the lightning strike here coming down, it looks similar to what we saw at that last strike once the connection's been made. Once the connection is made, all that energy that's in that channel flows to ground, starting from the ground of the lightning rod up. So we have, actually, if you look at it, and you could slow the current flow down, the lightning bolt actually illuminates in greater intensity starting from the ground up as the electrons flow through that from the ground up. Once we have that first flow, or what you call a return stroke, then we have another pool of energy inside the cell flow into that closed electrical circuit, and that current flow, that energy flow, is called a dart leader. And once it flows into it, it then funnels to Earth. That's a return stroke. So when you saw that flashing effect, it was the multiple dart leaders coming from the cloud through the channel and then flowing through the channel down, becoming a return stroke. And so you might hear somebody mention the word, what's a dart leader, what's a return stroke? The dart leader referring to the energy that's already in the cloud flowing into that closed circuit, and then the dart leader basically being the closed circuit the return stroke being that closed circuit, that lightning bolt, then being depleted of that energy. Now, in reality is, as mentioned from the bottom portion of the slide, the major problem we have for electronic integrity is not the direct strike. The lightning strike itself, in fact, we do a significant amount of business at refineries, at chemical plants, on platforms. And because the nature of the design of that vessel, that tank, that tower, it is a lightning receptor. It's over 3/16 thick steel. It's well grounded to the earth. It's not going to show any physical damage. And lightning rod's primary function is physical damage, not electronic integrity. What we're seeing all of our damage occur is in the earth current example, these next 4 or 5 slides, we're going to talk about what these lightning secondary effects are. This is what's causing the bulk of our problems from the standpoint of electronic integrity, maximizing uptime, ensuring reliability, and making sure that we maximize the efficiency, reliability of our site, of our facility, of our plant, of our refinery. It could be either earth current transient, an atmospheric transient, a ground potential rise, an electromagnetic pulse, EMP. These are the primary offenders when talking about electronic integrity. So let's kind of walk through these briefly. One of the biggest ones we have is a earth current transient. What's that mean? Well, let's illustrate here. Let's say we got a facility. It could be a gas processing facility. Maybe you have your command and control system here. You have inside this main building with the compressors is your control room. And the control room has a computer system, a PLC, possibly a DCS, and it's running underground conductors out to remote terminals, maybe to remote instrumentation control system in the field. Well, now we've taken our conductors and we've buried those conductors in the earth. Well, it's a good place to put them because they're out of harm's way as far as traffic, personnel traffic, truck traffic, and what have you. But as you go back to our first discussion we had about a cloud, our cloud has a positive charge at the upper portion of the cell. We have a negative charge at the bottom portion of the cell. And what does this negative charge do? It forces a positive charge on the earth and the earthbound structures. Now, that positive charge is forced on the earth, usually staying on the first few feet of the earth's surface. And where are those conductors? Well, they're buried in the first few feet of the earth. And this earth is working like a plate of a capacitor. It's holding a positive charge there. So now we're having this cloud move through the area concerned. It's building momentum. It's creating charge separation. It's getting ready for a lightning strike. It's forced a positive charge on the earth, earthbound structures. And now we have a scenario where the air can no longer work as an insulator. The air breaks down, and we have a lightning bolt developed. It propagates down towards the earth, and lo and behold, this tree actually develops a streamer that collects it. The building didn't collect it. The small remote building didn't collect it, but the tree did. But because of the proximity of that lightning strike to the tree and the induced positive potential that was on the earth, now I have a scenario where if I have a charge induced, this lightning strike, by its very nature of the basic theory and operation of electrical systems, now have to have that positive charge be neutralized. It's shorting out. So as I short out that positive and negative charge, all that positive charge that was forced on the earth surface now has to flow very quickly across the earth surface to the point of discharge, in this case the tree, in microseconds. And as that current flows very quickly across the earth surface, as you can see by this little yellow squiggly line here, we develop a voltage transient. This transient, high voltage, usually can be up to 10,000 amps induced voltage, probably 10,000 amps induced current at over 6,000 volts of induced voltage, gets reflected on these buried cables, goes into my remote terminal, maybe into my I/O cards, and three things happen. Obviously, the first thing that can happen, which is probably the most easy to understand, is you see the lightning, you hear the thunder, bam, you lost communication with a remote instrument, and you takes that system down, or you lost an I/O card. You hear, you see, and then you see the results, the smoke, if you will. Instantaneous failure. We like to call that again an instantaneous electronic failure. The second thing you can get is a false signal. We see this a lot in refineries and chemical plants where they're using maybe even triple redundancy transmitters. Well, they have an analog transmitter out in the field. The DCS is looking at that vessel and saying how much pressure is in that vessel or how much temperature. And it's got three transmitters, but if two of them spike high, it shuts that unit down. Well, now we've taken a high voltage and current, and we've induced it on that I/O, that instrument card. Now, these analog circuits typically run at 4 to 20 milliamps. 4 is a minimum, 20 is a max. So now I put a 2 or 3 kV voltage spike on that. I spiked that current to 20 milliamps for, let's say, a millisecond. Well, depending on how that DCS is set up, that millisecond 20 milliamp impulse could be seen as a DCS in this building here as a safety hazard, and it shuts the plant down. And so that tank might blow, I got to shut off. Well, when we shut the plant off, now we get a major problem with possibly having a product out of spec that has to be flared. We've now got a problem where we are not producing. We got to shut the unit down. So for the next 8 hours, I'm shutting it down and bringing it back up. So I'm losing revenues there and lost production time. And maybe there's a reliability issue. Maybe they had just enough product going out to their end user that he needs that product, but now he's got impaired reliability with his customer. He's not being able to ship what he's supposed to ship. So all those things can happen by just a false signal. So we have instantaneous failures, false signals, or which is a little more difficult to be able to address and analyze, is degradation. Even if we don't have an instantaneous failure, even if we don't have a false signal, there is still the potential for induced voltage and current on those low voltage data lines, instrument lines, analog circuits that will be reflected on these electronics, and that low energy impulse takes some life out of the electronics. It weakens it. It lowers its MTBF, mean time before failure. So all of a sudden we're having a very high maintenance cost because we're not getting the life expectancy we expect out of our electronics because they're failing due to this secondary effect. Now moving forward, you could have what's called an atmospheric transient. An atmospheric transient is caused by a transient that is actually developed in the air. So here we're showing you, and you might remember these squiggly lines, a very high electrostatic field developed. That's these little black squiggly lines here. Now, in this case here, we'll see a lot of power plants and chemical plants. They're using overhead cable trays. So here we're going to say these overhead lines are having communication lines on them. But what I've really done is I've taken my overhead communication lines and I've immersed them in a very high electrostatic field. For example, let's say this particular data line was 10 meters in the air, 30 feet. It's pretty much typical we see in a lot of applications. They're 30 feet up. And if I have 10,000 volts per meter of charge in the air, and I'm putting that cable at about a 10-meter elevation, it's basically immersed in a 100 kV field in respect to that elevation to ground. Well, now I'm having a lightning strike, and the lightning strike, let's say, wasn't even to the pole that was nearby. That field, which was there pre-lightning strike, collapses. That 10 kV per meter, let's say 10,000 volts per meter field, now collapses. And as it collapses, it induces an atmospheric transient on these overhead cables, which goes both directions and can cause, again, instantaneous failures, false signals, or degradation. We do want to make sure we use common grounding in our facility. We have our DCS here, our PLC in this, our computer system in this building, and we have our remote I/O shelter, field transmitters in this shelter. We do want to have ground 1 and ground 2 tied together. We do see on occasion that we'll still see somebody who manufactures a DCS say, hey, I want to have an isolated ground here. I don't want to have my ground tied to the plant ground. Well, you can keep it isolated above grade, but when you get in the earth, make sure you tie these two grounds together in the earth. Because if you don't, and you have a lightning strike to the building, and let's say this ground here is at 1 ohm, this ground here is at 5 ohms, we have 4 ohms of difference between those two grounds. And I have a 100,000 amp lightning strike here, rather rare. Let's actually use a 20,000 amp one for sake of discussion. 20,000 amp here is, Ohm's law says 20,000 amps on a 1 ohm ground, E voltage equals I current times R resistance. That's 20,000 volts on ground, this ground here. This ground here is going to be filling the effect of about 100,000 volts because 100 kA strike, 5 ohm ground is 100 kV. So now I've got a difference of potential between this ground and this ground of about 80,000 volts. And I got a resistance between the two, which is ground, or my shielding effect, my shield itself. That difference of potential is going to want to get neutralized, and it's going to go either through the earth itself or, worst scenario, through our electrical system like our shielding, which can cause electronic damage. So we want to make sure that we keep all grounds at our facility tied and bonded commonly together. An electromagnetic pulse, EMP, is caused by a lightning strike. Now, to get an EMP of any significant value that would affect our electronics from a lightning strike, we have to have a pretty significant amount of current. Let's say around 100,000 amps lightning current. Again, as I mentioned, probably about 5 out of 100 lightning strikes equal 100 kA, 100,000 amps or greater lightning current. So they get quite rare. But if we did have a high lightning current strike and its rise time was 1 microsecond, we would have a significant electromagnetic pulse developed. As that lightning strike, in this case here, we are showing you an example of lightning hitting my lightning rod. The lightning rod's done its job. It's collected the strike. It's taken that current to ground. And as it takes the current to ground, because of its current maximum flow, 100,000 amps, and its fast rise time to the 100 kA peak, we develop a significant electromagnetic pulse, inducing a voltage on all of our interbuilding wiring and creating electronic failures. So in review here, we have earth current transients, atmospheric transients, electromagnetic pulse, and ground potential rise, all being really the major problems with lightning-induced problems. As I mentioned, here's some quick lightning data. Peak current from 2 to over 500,000 amps. Reality is, 1 out of a million might be in that range there. Most of them are between 2 to 200 K. Example we might see here at 99% or 200,000 amps or less. We're averaging around 30,000 amps, mostly negative current, and it's a high frequency. When it discharges, it oscillates, so it's running at 200 kilohertz to 20 megahertz frequency. So when you're dealing with lightning protection, you want to use a low inductance cable, because if you use a high inductance cable, you're going to have an issue with a high impedance developed on your cables, lightning current seeking the path of least resistance, may not flow through your preferred path, your cable, and flash over onto other electronics that you don't want to have. Now let's talk about strike collections and the fallacies of some lightning collection devices. Now I mentioned briefly earlier that there's a couple of standards out there. These are only dealing with conventional lightning rods, NFPA 780, UL 96A. Those are lightning rod standards. Their main mission is collection. It's based a lot on historical, grandfathered in design. Not a tremendous amount of scientific data applied to it. It's a lot of basically trial and error over a 200-year period. Who is really the father of the lightning rod? Well, some of you may know that it actually was Ben Franklin. Ben actually did create the lightning rod back around 1760-ish. In fact, when Ben first came up with his theory on a lightning rod, he thought a sharp point would actually dissipate a storm cell. Not quite so, but he was right about ionization flow off a sharp point. He linked lightning to a charge. He was correct there. Lightning rods were intended to discharge a cloud, as I mentioned, to dissipate. Found out very quickly it wouldn't do that, but it worked as an excellent lightning collector. And he invented the lightning rod back in the mid-1700s. Now, as I mentioned, the lightning rods by themselves don't have sufficient capabilities to dissipate a storm cell. They did protect structures, as I mentioned earlier. Lightning rods are 90 to 98% effective in preventing all lightning from striking the protected area. Now, it still may, it would have the adverse secondary effects: ground potential rise, EMP, earth current transient, atmospheric transients. They're also going to be there with a lightning rod, which again is our primary problem anyways. Now, it works as a great termination point for a lightning strike, and really designed over time with experience. Here's examples of lightning rods. The question we had about damage to a lightning rod, you can see they're designed actually to be able to take a actual strike and not have any problem itself. These are ESC devices. ESC devices are, and I'm not going to spend a lot of time on those because of time we have, but they're glorified lightning rods. They basically say one of these devices is all you need for protecting 60-meter radius, and I don't even worry about strike zones. So those are somewhat controversial. We don't get into really debating the performance of those issues. The bottom line from our perspective is, do you really want to collect lightning at all? And these devices are lightning collectors. Here's an example of a lightning damage to a chimney. And this actually is an ESC device. Now, most ESC devices only go to around 100,000 amps. Over 100,000 amps, you see what happens to the device. It burns up. Some examples of lightning striking an actual pole. Here's my lightning rod, but it missed. The pole missed the rod, hit the pole. So again, lightning rods aren't always the most effective in collecting all strikes. This is actually an illustration of a petroleum fire. As I mentioned, millions of dollars of damage. We had a customer we worked with a number of years ago. We were not protecting this tank, but it got struck in the Midwest, and it is holding, I believe, a regular car fuel, process fuel, and completely burned down. Now, two things I want to point out is the magnitude of the fire, as you can see here, at this particular tank terminal. And this actually is, you can see the actual area of influence around this one lightning strike. We have quite a large area of influence this one lightning bolt could have struck. It could have been miles in radius. Keep that in mind for later on. Here's that tank that just burned in the previous photograph. We were told that by itself, the loss with the product and the tank was around $3 to $4 million in that one tank fire. Then they had to clean up and other environmental issues, which they figured was probably under $4 to $5 million. So they're approaching, in their mind, close to $10 million hit on this one tank fire. So one lightning strike, in this particular case, easily reached 5 and approached, according to the client, close to $10 million. Here's examples of some lightning strikes that occurred at gas facilities. The strike ignited the gas main and basically burned the facility up tremendously, total loss of the facility. The heat was so great it burned that car that was parked some distance away, basically totally burned out that car and damaged it. So, strike collectors increase the risk. We don't really want to have lightning activity in an area where we have either explosive or electronics. Let's talk about direct strike protection. We look at things alternately. Rather than trying to collect lightning, let's try to prevent a lightning collection. Let's create an electrostatic environment that's not conducive to lightning collection. Now, as I mentioned, we've been around since 1971. Our systems have a 99.87 success rate, and with the success rate, preventing all collection to our protected zone. That's how we describe and define success rate. Over 40,000 system years, and we offer a exclusive no strike warranty when our system is installed under our supervision. Now let's talk about some basic principles of this technology. Lightning is discharge. We're taking basically 20, 30, 40,000 amps and transferring that current in the course of microseconds. Our system is we call a charge transfer system, but rather than taking that energy over microseconds, we're going to constantly and continually discharge the site during the course of the storm. Generically, we call it a charge transfer system, CTS. Our patented name is the dissipation array system. We're going to use a known phenomenon as point discharge to make an optimum ionizer to be able to dissipate our site. And I think I'm on a 2-slide forward here. Pardon me on that one. Here's an example of my test simulator in which we're showing you and I'm going to recall my slides.
Peter, I think sorry to interrupt, but I think you may have accidentally hit the sync button. Can you try hitting that again?
I might have, yeah. How can I turn that on? Hit again?
Yes. It should be dark. There you go.
Yeah, thank you. Anyway, that said, let me back up a couple slides here, if I can. We're going to use a known natural phenomenon called point discharge, which allows us to actually dissipate the use potential on the site. And I'm not backing up here, though. I don't know why I'm not doing that. I don't know why I'm doing this here. I'm pushing the back arrow.
Are you pushing the left arrow?
Yes, I am. Previous. Now we're going backwards, I think. Here we go. Pardon me for a small delay here. Thank you. So anyways, back on track here. We're using a known natural phenomenon called point discharge. Point discharge, very simply, is if you take a sharp point and you immerse that sharp point in a high electrostatic field, electrons are bled off by ionizing the air molecules around the point, and you have a current flow, you have electron flow. Here we're showing you a simulator where we're actually showing you the visible corona off our system, and it still wants to slide forward on me pretty quickly here. So I don't know why it's still on a timer here. It's going very quickly forward.
Oh, you know what? I hold on one moment here. Let me fix this for you.
So anyways, with that said, let me kind of back up. What we're doing is we're going to create a natural, we're going to take the natural event of ionization. Ionization is a very simple, natural, known phenomenon, which says, again, if you take a sharp point and you immerse that sharp point in a high electrostatic field, and by the way, we know that during lightning, there is going to be a very high electrostatic field. Going back to my first 2 or 3 slides, we showed you that to have lightning, we have to have at least 5,000 volts of electrostatic potential to have a lightning event. So you take a sharp point and you immerse it in that high electrostatic field, you're going to bleed off electrons. Remember now, electrons, what creates charge separation? You have too many electrons or not enough. So what you want to do is we're going to bleed off electron flow where there's too many electrons, and we're going to transfer those electrons to a point that doesn't have enough electrons to neutralize that field. And that's where a dissipation charge transfer technology works. So back arrowing up here. So here's an example of our wire, multi-point ionization wire. In a field simulator, we can develop 50,000 volts of potential between those 2 plates. This slide here, we've actually activated the planes, indicated plates. We have about 30,000 volts of potential between the top plate and the bottom plate. And that blue glow is actually a cold corona off those points, showing you actually a dissipation, electron transfer off the ionizer. That's actually an example of an active system in the field. Let's walk through the system real quick. Now, first of all, this technology is not, as far as scale, it's not the right scale. You might see a little umbrella here, which looks like it's quite large, but reality is it's way too big as far as reality. That's not to scale, to say the least. But it gives you a good visual. Here's our ionizer. What's an ionizer supposed to do? Looks like we've got the ionizer working here to where, again, the ionizer is a device that is designed to create electron flow, taking it from a place that has too many electrons, if you will, to a place that doesn't have enough electrons. And this is going to be a device which creates that electron flow, that current flow. Now, moving forward here, what we do is the storm moves into the area. We're a grounded product. So your ionizer is, in this case, on top of the tower. It's tied to earth ground. As that thunder cell forces that charge on the earth, we collect that charge and slowly and continually funnel that charge slowly and continually and methodically throughout the course of the storm. So we have this electron flow occur to a point that has too many electrons to a point that isn't enough. We neutralize the electrostatic fields. We lower the fields in the protected area. And here we're showing you the dark squiggly line showing you high electrostatic field intensity outside the protected zone, but a very minimal electrostatic field, let's just say 5 or 10,000 volts per meter, inside the protected zone. We don't want to have a scenario where we could generate a streamer from our zone. If we generate a streamer in this zone, we have now acted like a lightning rod, which is what we don't want to do. Now we're seeing that actually this thunder cell has developed a lightning bolt, a leader, and it's propagating down towards the earth. It's kind of heading towards our protected zone and heading off-site. As I mentioned, the area of influence of a lightning strike could be over a mile radius. Here we're protecting an area, let's say about a 100-meter radius. So now we are now dissipating the charge. We're creating an area here which is not going to allow streamer generation. So as this leader even approaches our protected zone, we cannot develop a streamer. But now, let's say a quarter mile away, the smaller shelter over here, outside of area concern, has now actually developed an upward streamer. And by creating this low electrostatic field environment, by dissipating, by ionization effect, by neutralizing the electrostatic fields in this area, we're not going to develop that streamer, which now allows the streamer off-site to win that race. And now we have determined point of collection. And all the energy flows over here, not in our area of concern. So therefore, we're not going to feel those negative secondary effects of earth current transient, atmospheric transient, electromagnetic pulse potential, ground potential rise, because we have not had the collection in our area of concern. So the real simple approach is, do we want to collect lightning, or do you want to create an environment that's not going to be conducive to lightning? And that's what this technology does. Back in 2007, we did some testing in Denver at one of our customer sites. As you can see here, they had a tower. This tower, this building, is protected with our dissipation array. It's been protected since about 1990, as a matter of fact. We also put a voltage field meter to measure the field intensity outside the zone and inside the zone. And what we measured was the electrostatic fields in and outside the zone. And you can see here that, for example, in this particular illustration here, we had field intensity in excess of 20,000 volts per meter inside the zone. Probably outside the zone. Outside the protected zone, the blue. The blue is outside the protected zone. But inside our protected zone, the voltage intensity in the air is around 7,000 volts per meter. Significantly less than outside the zone. So you can see the neutralizing effect that we've created by this dissipation technique, lowering the fields. By lowering the fields, you don't collect. Now here's an example of we did with one of our other customers, who actually happens to be a very well-known customer, Tennessee Valley Authority, TVA. The Brownsbury plant in Alabama, the nuclear power plant, bought a system over 10 years ago, and their engineer ran a test using their lightning data, tracking storms, to find out how effective this technology was in reducing the lightning events in their area. They ran a 6-year timeline, 3 years before the installation of our dissipation array system, and 3 years after installation. And they ran a lightning activity radius. In other words, they recorded lightning strikes cloud to earth at a 500-meter radius, 3-mile radius, 6-mile, and 10-mile. And the array, by the way, is on a 600-foot stack, our system. Now, here are the envelopes of those years. Again, this is 3 years prior. 40 strikes inside the first 500 meters. Then we had 2,630 lightning strikes inside the first 3 miles. 11,277, 6 miles, 33,685. So, again, breaking this down, in the first 500-meter radius, they recorded 500 cloud-to-earth lightning strikes in that first 3 years. After the installation, they recorded 13. Now, by the way, our protected zone is only right in here, about a 100-meter radius, which they didn't have any strikes in that radius. But it also shows the fact they reduced lightning strikes all totally around the plant. Now, one might say, well, it's because there wasn't that many storms those last 3 years. Well, if you look at the actual 3-mile, 6-mile, and 10-mile, on that same after installation activity, we actually had an increase of cloud-to-earth lightning in the area for those 3 years after. For example, 3 years we had 4,327 cloud-to-earth strikes, where in the previous 3 years, before installation, we had 2,630. So we actually show more lightning in the area, but much less, none in the zone, and very little around the protected zone. Again, proving that the system does prevent lightning activity. And this is an independent test run by Tennessee Valley Authority. Here's an example, again, in a table format. Considering time, I'm not going to go too much detail, but it just outlines the number of strikes that I just went over in the envelopes. Now, when you look at a lightning strike plan for any facility, you want to look at all the points of vulnerability. And from that standpoint, we want to make sure that we do have everything covered and at least addressed and talked about. For example, we like to describe lightning as 3 legs of a stool. And we're resting our protection on those 3 legs. The 3 legs of the stool being direct strike, Second leg of the stool being surges on AC power, data line, control lines, and the last one being proper grounding and bonding techniques. Even with a dissipation array system, we can create an envelope over a site that is going to give complete lightning isolation. But if you have a lightning strike that's from outside the zone, we can have lightning be induced on our AC power from the power lines feeding our facility. So we have to be very careful about, making sure we have that covered here. So again, any power line that's entering our facility, because it's entering from outside a protected envelope, should have AC power protection. So again, we have products that you can apply to the main AC panels or your sub panels, whether it be a Facility Guard, which is a panel product, or a TLX 100, which is a nipple-mounted device for a sub panel. We have products to put on those areas of vulnerability if the power line is coming from outside the protected zone. Again, so what are we trying to achieve? Our points of vulnerability being direct strike. We want to put dissipation array in our building. Induced voltages coming from outside the protected zone. Do we have proper AC power protection? Do we have proper protection on our low voltage circuits? All of our instrument lines could be vulnerable to lightning events. Again, if that instrument's outside the protected zone, that shelter's 100 meters away, and we're only protecting the building, we need to put low voltage protection on those low voltage lines, because they still could have a lightning induced transient from outside the protected zone. So we look at a site and say, okay, what are all the potential points of vulnerability? Low voltage lines, AC power line. Are we creating an envelope of prevention? If we are, what's that zone? What could then penetrate that zone? And then from that, we develop if some augmentation might be necessary. We have some clients that say, listen, we don't want to worry about the direct strike. We just want to apply surge protection, whether it be for the AC power or for the data lines. We want to apply strategic surge protection, and we'll assume some risk on direct strike collection. Well, that is an option. Some clients want to do direct strike protection with enhanced grounding. Do they have good grounding and bonding techniques? We have found that from our perspective, that we want to make sure that we have a low impedance ground in which we bond our electrical systems as well as our lightning protection system. Even though the standard, so you might see, say, 25 ohms for our ground grid earth contact, we like to shoot more for a 5 ohm because, again, when you have a lower earth connection, a good ground grid to bond your electrical and instrumentation to, you're going to minimize the potential effects of a lightning strike. So we want to address that, and in many cases we'll look at using, for example, what kind of down conductors are you going to use? Are you going to use existing building steel as your down conductors, which you can use? Do you need to run a dedicated down conductor? Sometimes we'll use in existing building steel structures. If it's continuously electrically conductive from the top of the building to earth ground, you can use building steel. Or if you're not sure, you may want to use a dedicated down conductor, a low impedance down conductor. If we don't know how good our building steel is, we will add a dedicated down conductor. In our gas plants and our in refineries, typically we will bond to the existing steel tank vessel structure because they have such a steel mass there. It's perfectly acceptable. In a fiberglass tank gas facility, an SWD site, which is a salt water disposal site, well, we will then use dedicated conductors because obviously fiberglass is not conductive. So we could use all of that. We also want to make sure we have a unified earth connection and all of our grounds tied together. Very important that we have common grounding and bonding techniques. So we're having everything in our area concerned all tied together correctly, and if there is a lightning strike, we like to describe it as all rising and falling. All of our grounds potential rise and fall at the same potential, so we avoid a difference of potential between grounds. So that's also very important in our system. So again, are we using adequate technique in bonding and grounding? Do we have a good low impedance ground? In some cases, if we're and what's going to govern how good my ground grid's going to be? Soil resistivity. How conductive is my earth? And our soil resistivity in the United States varies dramatically from minimum to maximum. For example, we can have soil resistivity of less than 5 ohm meters, 5 ohms per cubic meter of earth, to over 5,000 ohms per meter. Well, trying to get a 5 ohm ground if you're in 10 ohm meter soil is very easy. Basically, one ground rod does it. One 10-foot ground rod, you're there. But trying to get the same 5 ohm ground in a 5,000 ohm meter is a much more difficult challenge. And if you get high soil, dry soil, rocky soil environments, West Texas, parts of Oklahoma, the Rocky Mountain area here, you're not going to be able to do that with conventional rods. You may have to look at alternative grounding methods like a chemical rod technique. And those are things, too, we look at is how effective is your ground and how effective is your soil that you have to get that good ground. So those are things we look at. And again, that's where if you have a high soil resistivity, a chemical rod, as in a chem rod, which actually treats the earth, these little copper pipes right here are examples of a chemical rod, a chem rod. What they do is they actually treat the earth and make the earth more conductive, increasing its rho, which is conductivity, thereby allowing us to get a low impedance earth connection even in an adverse soil condition. Now, how many chem rods you might need is predicated on what your soil resistivity is. If you're only at 50 ohm meters, you might only need 1. If you're at 200 ohm meters, you might need 5 or 6. It's a non-linear problem. The greater your soil resistivity, the more rods you need. It's not a linear, so you could actually triple your number of rods when you double your soil resistivity. Those are all things we look at. So when we look at a facility in review, we want to look at all of the points of vulnerability. And that being direct strike, AC power, which would be your panels, sub-panels, transformer location, we call category C location. Those need to be considered. Are they vulnerable? Do we want to put protection on those? Are we worried about low voltage circuits? Would they be, again, low voltage would be our instrument lines, control lines, analog, data, digital. Those are all systems that could have a vulnerability. And in fact, our low voltage circuits are going to be the most vulnerable because they're used to operating with voltages of 5 volts or less and currents of milliamps. So any kind of voltage impulse on that low voltage line could cause instantaneous failures. So these tend to be the most vulnerable, AC power being a little less, but still a concern. We do have, whether it be AC power, facility guard, transient limiters, power DINs, DC power supplies, your low voltage analog, digital circuits, all of those could be addressed. And in our particular case, we do have products that will address each one of those needs. Grounding. Do we have good grounds? Are we using good, adequate bonding interconnects between grounds? Are they the right size? Or do we have a good earth contact? Is our soil resistivity good? If it's good, we can just use standard conventional copper-clad rods. If it's high in soil resistivity, we may want to consider augmenting that with a chemical rod to ensure we get a low impedance ground. So you got the grounding is a concern. So we look at our area protection. We want to look at all the points of vulnerability. So from our standpoint, kind of in summation here, what we look at is trying to provide a unified systems approach in lightning protection. What's available? You have collection systems work very effectively, but you have the risk of a scenario in which you're inviting a lightning strike, which has a tremendous amount of energy meaning voltage and current with it. And depending on your operating systems and your environment, a induced voltage and current could be very negative and have a significant adverse effect on the operating systems, whether it be on our command and control systems, or in some cases we've been involved with, if you have a explosive environment where you have vapors either present part or all the time, any kind of a spark could be catastrophic. And therefore, a conventional collection system wouldn't be appropriate. If you're worried about just structural integrity, conventional lightning rods are very effective. Price-wise and performance-wise, that's the right solution. But if you're looking at for a sensitive system that has instrumentation, in most cases, lightning rods aren't the right way to go. You need to consider alternative methods. And what we do from our perspective is we try to lay the foundation for these are your alternatives, these are your risks, these are your benefits, and apply a system solution based on each particular customer's concerns and goals and protection. And that's it. I don't know if we have any.
All right. Well, thank you very much to Peter Carpenter. Did you want to go over your last few slides, just the images, so that our audience knows what they are?
Well, I'm sorry. I didn't know. I apologize. Yes, thank you very much. I realized that we didn't have a few application slides here. They gave me about 2-3 minutes here. Let me just do that. We have some examples here of the dissipation rate technology in industrial application, where it'll be in a petroleum environment. And if you can see the little umbrellas here, and there's also some ionizers, again, going back to that ionization term, throughout the plant. And we can actually develop and grow a envelope protection throughout a complete refinery. And this is an example of a dissipation array system in a petroleum processing facility. You can also put them in airports. One of our biggest customers lately, last 20 years, has been Federal Express. We are protecting pretty much all what they call critical sort facilities in aircraft and avionics at their main Memphis mega hub in Memphis, Tennessee. We've been out there since about mid-1980s, and constantly buying more systems from us as they grow. In fact, every year we have numerous orders from FedEx. We also are doing the UPS structure sort facility in Louisville, Kentucky. Some examples again of their facility, their flight line, and some of the arrays. Tank storage. We do. It could be used tank storage for floating roof tanks, fixed roof tanks, fiberglass tanks. Again, any kind of lightning strike to a tank could have either failure of transmitters, control circuits, or Lord forbid, explosive results. And this is going to be an oil store facility, happen to be Lagavon in Venezuela. We've done data centers. You have computer facilities. There happens to be one down in Jacksonville, Florida, a very high lightning area. We can do, this happens to be ExxonMobil down at Mobile Bay, Alabama, having our arrays on top of these mobile structures. Again, giving a whole area of a lightning prevention. An old NASA tracking station down in White Sands, New Mexico. Here we put this tower in, a small round tower in, to create an envelope over these dishes. So we're protecting this whole facility, and we did add this little array to provide the envelope of prevention. PPG, Lake Charles, another facility we did. It's been there over 20 years, and we actually have constant business with PPG. And this is preventing ignition of their H2 stacks, their hydrogen stacks. Any lightning strike in the area would ignite these stacks, obviously causing a very high concern for explosive environment in a hydrogen-rich area. So we protected those stacks, preventing them from igniting by lowering the electrostatic fields when using this ionization dissipation array technology. Turner Broadcast has quite a few facilities using our system. I don't know if that slide's coming up here. Here it is, showing you example of an array in the background. And we have about 3 of their major broadcast properties in the greater Atlanta area protected with our technology. That's going back to about since 1990. And offshore platforms. You can see some of our ionization here. We've done quite a few offshore platforms around the world. A significant amount of those are off the west coast of Africa, in Malaysia, and in the high, we like to call the high isochronic, high lightning areas of the world. And the whole objective there, too, is to provide a lightning-safe environment to maximize reliability and uptime of these platforms, where any kind of downtime could be extremely expensive, let alone the risk of a lightning strike into personal safety. This slide actually having in Papua New Guinea, which is one of the slides one of the locations we protected some years ago. That just happened to flash off the screen. I'm not sure why. Stack protection, example of how big the system can be on a stack. And you can see literally the thousands of points This particular array is probably somewhere in the order around 15 feet in diameter, and we'll have somewhere around 5,000 feet of wire, and somewhere approaching 30,000 points, sharp points on this array to provide all the ionization electron flow that we need to dissipate and neutralize that field intensity. Happen to be at a paper processing facility in the south. So there's kind of a quick review of what we've done worldwide over the last, really going back to the mid-'70s, and we appreciate your interest. And if there's any questions or you have down the road, I'm sure that we will be able to get you some information to get a hold of us. And if you have additional questions that were not addressed during this presentation, I'm sure we'll find a way to get those questions answered through a personal email and or other mechanism. Thank you.
All right. Well, thank you very much to Peter Carpenter, and thank you to our audience for your participation today. If you are new to EUCI and would like to learn more about our other offerings, please visit us at www.euci.com. This will conclude today's web conference. Thanks again to Peter for an informative presentation, and thank you again to our audience for your participation today. I look forward to seeing you at future EUCI events, and we will now close out today's meeting room. Have a great day, and thank you, everyone.